Hello and welcome to this Tuesday webinar series with EasyPower and Bentley Systems. My name is Ian Higginson, Manager of Consulting for the User Success Services Americas region for Bentley Systems. Came over with the acquisition of EasyPower, and my background is in electrical engineering, so standing in for Jim, the normal presenter, Jim Chastain today, so you maybe have not heard my voice before, so hopefully this will be an interesting session, and we're going to cover Introduction to Cable Ampacity Rating with EasyPower. So let's go ahead and get started. So today's discussion will be broken up in the following categories, starting with a brief discussion of cable ampacity basics. We'll then talk about the Neher-McGrath method for estimating cable ampacities, which relates to NEC NFPA 70E and its cable ampacity tables. There we go, to follow along with the slides. Next, the NEC approach to cable ampacity rating based on ambient temperature and standard cable installation type will be described. And you attendees will learn how to apply these concepts in the EasyPower software. Finally, we'll give a live demonstration and have some time for questions at the end. So put simply, cable ampacity is the current carrying capacity of a cable. The current magnitude of a cable can carry is based on the allowable maximum operating temperature of the conductor inside the cable, which is often something like 75 or 90 degrees C in the United States. Continuing operation above a conductor's maximum operating temperature will cause premature cable aging and insulation degradation, which leads to failures like short circuits. Practical application has also shown that the insulation medium, such as direct buried, installed in ducts, trays, open air, etc., and external sources of heat, adjacent cables, for example, can significantly limit a cable's ampacity before the conductor reaches its maximum operating temperature. EasyPower's cable derating feature accounts for some common cable installations, and we'll discuss and demonstrate that on presently. There are few methods out there for calculating cable ampacities, all of which are based on heat transfer equations. IEEE Standard 835 describes the Neher-McGrath method in detail and provides calculations for some example cable installations. This is the methodology recommended by the NEC for determining cable ampacity and will be described briefly. IEC 60287 also provides a methodology based substantially on the Neher-McGrath method, with some differences in how heat sources are treated by the method. For complex cable systems with arbitrary geometries, there are finite element calculation methods that you can use to determine the maximum operating temperature of the installation, which you can then back calculate the ampacity from. So the Neher-McGrath method, we're going to talk about that primarily because that's what the NEC specifies for calculating cable ampacity. So this method relies on a hypothesis known as the Kennelly hypothesis. When in relation to electrical cable systems, the hypothesis is that thermal resistances exist between the conductor heat source over here and the ambient environment over here. Using this assumption, we can represent heat transfer equations as thermal circuits here. So what happens is that the flow of heat generated in circuit W, which is analogous to electrical current in some ways, will propagate through a equivalent thermal resistance here, RCA, and then be dumped into the ambient environment here. The heat is generated by I squared R losses in our conductors primarily, and our ambient temperatures are fixed at some temperature, usually 30 or 40 degrees C. So the conductor temperature overall is dependent on the heat produced by our sources of heat, e.g. our cables and their loading, and then the thermal resistance of the insulation medium. So the equivalent thermal resistance that restricts our heat flow are things like the cable insulation itself, what wraps around the conductors, the medium in the duct, so if this is air, some kind of gas or oil, etc., the duct walls, the walls of the duct, again, assuming these are in some kind of duct bank installation, these cables, the duct bank material, if it's encased in concrete, and then soil as well, if these are buried. will all contribute to the equivalent thermal resistance in our heat transfer circuit here. So hopefully the math on these next two slides won't be too egregious, but we'll go through it anyway. So based on that previous slide, the heat transfer circuit, we can write the Neher-McGrath equation in this form, where we've got conductor current multiplied by resistance to give us our I squared R losses, then again multiplied by the thermal resistance of our circuit, and that's going to be equal to the difference in temperature between our conductors, what they ultimately will rise to when they're conducting load currents, and then the ambient temperature. In this step, they also add a correction factor to this equation, which is the dielectric loss temperature rise factor. It is basically the heating caused by very strong electric fields. So if you are working with cables below 46 kV, this basically will drop away to zero, and we're left with the equation we saw from the heat circuit on the prior slide. So if we solve this equation for current, we'll get the form of the equation that's shown in the NEC. And the other change that they make at this point is we'll swap out the AC resistance here for a DC resistance value for the cable multiplied by a correction factor, which is due to the skin effect and proximity effect of the cables to one another. So that will increase the resistance compared to the DC resistance somehow. So if we have a fixed value for conductor maximum operating temperature based on the cable design, again 75 or 90 degrees C, and we assume a fixed ambient for the environment, a fixed temperature for the ambient environment, then the only really unknown in this equation, assuming we know the DC resistance of our cable and can correct to make it the AC resistance, is the equivalent thermal resistance of our cable installation. So this is the tricky value to obtain, especially for complex arbitrary cable installations. However, fortunately, the NEC has taken care of the work for us by providing tables of ampacity values for a large variety of cable types, as well as some configurations of common cable installation configurations that we've incorporated into the EasyPower software. So speaking of NEC articles, let's discuss those in brief, how they play into the EasyPower cable ampacity derating discussion. So first, we have Article 310, which contains information on conductors for general wiring up to 2,000 volts. Then we also have Article 315, which is for cable installations between 2001 and 35 kV. So the ampacity values in EasyPower software are extracted from tables listed in Article 310 for below 2,000 volt cables, and these are the tables 310.16 through 310.20. For cables between 2,000 and 35 kV, the software is referencing tables 315.60 C1 through C20. The cable we also reference for multiple conductor installations, such as those commonly found in cable trays. The software references derating values that you can locate in table 310.15C1. Lastly, there are some, within Article 315 as well, there are some cable installation details that EasyPower will also take into account when correcting for common installation types. So these are going to be demonstrated on the next few slides. So the cable ampacity details available that are described in the NEC are shown here. 4 of them are shown here. These details are linked to NEC ampacity tables with specific dimensions used as shown to calculate equivalent thermal resistances, which then allowed them to calculate the ampacity values. These are intended for use with the NEC tables 315.60 C11 through C20, but their use is also extended to lower voltage installations by the software. Detail 1 is for a single 3-conductor circuit, and which forms the baseline that was used to calculate the ampacity derating multipliers for details 2, 3, and 4. Detail 2 is a duct bank with 3 ducts, 3 circuits. Detail 3 is a 6 ducts, 6 circuits, and detail 4 contains 9 ducts. So recent editions of the NEC do not include detail 4, but EasyPower retains the derating multiplier for this installation since the NEC isn't retroactive, so that equipment installed under prior versions of the NEC can be assessed at using the same edition of the standard that was in force at the time. So we retain this installation detail as well. So for buried conductors, the prior details were for duct bank installations. So for buried cable installations, EasyPower has two derating options, which are details 9 and 10. Detail 9 is the single conductor or single circuit, 3 single conductor cables in one circuit. Detail 10 would be 2 circuits with single conductor cables. Similar to the D1 through D4 derating multipliers, the detail 10 is baselined from detail 9 here. Reproduced here is NEC table 310.15C1 from Article 300. These derating values are for applications where there are more than 3 current carrying conductors, such as in cable tray installations commonly. The percent derating values shown here. For derating, we provide 2 entries within the EasyPower software labeled tray 1 and tray 2. Tray 1 is for up to 6 conductors, and tray 2 would be for up to 9 conductor installation. The table of derating factors in EasyPower also provides numerous entries where you can create user customizable inputs, which we'll show during the live demonstration here, if you need higher cable fill deratings. So speaking of the device library, this image shows the cable derating factors table that's included by default with the program, which is based on, again, these NEC details that we just discussed. So users can include additional derating factors for commonly used cable installation configurations by filling in these blank rows here. The device library can also be accessed by clicking the File button, File menu button within the program, and then selecting the Open Device Library and choosing to open your standard device library, which is what we're going to show in the example coming up. So to actually set up cable derating in EasyPower, we first need to choose whether or not we want to adjust based on ambient temperature of the cable installation, which is also included in the National Electrical Code. The default setting in our program is none, which means that the cable ampacities are based on an assumed 30-degree ambient temperature. If we set up US as our ambient temperature derating, that means we're going to use the NEC adjustment factors, which can actually include increasing cable ampacities if we assume ambient temperatures are lower than the default value. So we use NEC table 310.15B11 for adjusting cable ampacities. We can also adjust cable ampacities within the program based on this equation here, which the adjusted ampacity I prime is based on different ambient temperatures, TA prime. So the program will switch between these two depending on whether or not the ambient temperature you specified is a standard one from the table or is not present in the table, in which case this equation is applied. So it gives you a broad coverage of possible ambient temperature corrections here. So getting into the actual setting up cable ampacity rating on a specific cable, we have to do that from within the cable dialog window under the Specifications 2 tab. Shown here are the default configurations for EasyPower that were mentioned previously. D1 through D4, D9, D10, tray 1, and tray 2 are selectable for derating based on configuration, and then the ambient temperature derating is also included in this tab as well. So now we're going to go ahead and move into the EasyPower software to reinforce our understanding of this cable ampacity derating topic. So excuse me for one moment while I switch into the software. We're going to take a look at the bigger.dez sample file, which you can get to from the File Open File menu, and then going into our samples directory, opening bigger.dez. We're going to take a look at the feeder cable off of switchgear 5 out to MCC 5A. So if I double click on the feeder cable here, we'll see the standard ampacity for this RHH cable is 350 amps. It's a 350 kc mil cable at its maximum operating temperature. Down here at this 75 degrees C value is for the termination points of the cable. So as we can see here, the ampacity is a little lower at the terminations, which is often the case. So you may want to be careful that you're not exceeding this ampacity, which may be slightly lower than the corresponding cable's maximum ampacity. The value here is initially affected by these raceway or installation selections. This cable was installed in steel conduit by default, but if we switch this to an air installation, for example, we can see the ampacity increases because the cables installed in air have a lower thermal resistance than cables in the same cables in conduit, so they can be loaded up to a higher amperage before they hit their maximum operating temperatures. If we want to derate this cable installation, we have to click on our Specifications 2 tab, where we see the ampacity derating section here, which is where we can select the common duct configurations. You'll see D1 through 4, D9, 10, and then the tray configurations. So if I imagine this is a D3 with 6 cable feeder conductors in a single conduit, we'll come back to our Specifications tab, and we can see that from 350 amps, this cable has now been derated to only be capable of carrying 214 amps. Similarly, we have also derated the terminations down to 189 amps. We'll see here the default ampacity of 30 degrees C. If I adjust this value, I don't get any effect for the cable. It does adjust the terminations, but it didn't derate the cable ampacity further. So if I want to get this value to also derate my cable, the ampacity estimation, I need to come into the Tools Options tab here and then change this cable derating based on drop-down menu to be US or Canada if you're using the Canadian electrical code, but I'm going to use the National Electrical Code, NEC, and apply the US cable derating correction factors. So we can see here that now if I go back into this cable, the ampacity has been further derated from 214 amps down to 194 amps. So we can go the other way too. If I decrease the temperature below that to a lower ambient than the default, we can see the ampacity actually will increase on this cable up to a higher value. So you can play around with these two effects, and they can generally the duct configurations will lower your values, and the ampacity ambient temperatures also will generally lower your ampacities, but in certain cases can cause them to be a little higher for special circumstances with colder ambient operating temperatures. So the last thing to show is in our device library up here. If we go File, Open Device Library, and then I select our standard library, we get a table we get our device library window, and we can open the cable derating section right here. And as we can see, there is a option for US derating factors, where all the default derating factors are kept that are present in the drop-down menu, including, and then I added another entry to this table to replicate what a user could do to incorporate more derating multipliers. So I just called it tray 3. I said it's for 10 to 20 conductors in cable tray, and I gave it the derating multiplier of 0.5, and so that is based on the similar NEC table referenced earlier. So with those values added to my library, when I come into the cable, you can see I have the option for that tray configuration in my drop-down menu now, and that will derate the cable accordingly. So that concludes our live demonstration of the cable derating features with EasyPower, and also concludes the webinar portion as well. So I want to thank you very much for your attention and attendance don't hesitate to contact EasyPower at these email addresses shown to be in touch. Don't be a stranger, and we'll see you next time. Thank you for having me today, and hopefully you have a great rest of your day and a